right. Welcome, everyone. The door's closed. That must mean it's time to get going. So here we go. Welcome to Connect 2017. Hope you enjoyed the keynote. Delighted to see so many people here. So here we are to kick things off on the architecture track. We've got a great set of sessions and talks coming up across the conference, but particularly on this track today. So we're here to give you a broad overview. And along the way, we're going to point out some of the other sessions coming up further on in the day that you might be interested in. So for those that are new to Couchbase, we're looking forward to telling you our story, showing off our features, what we're capable of. And for those of you that have been with us a while, we're excited to show you what we've been up to over the last 12 months. A quick introduction. I'm David Haikney. I'm the Director of Engineering for Couchbase, based in Manchester in the UK. And alongside me is my colleague Dave Rigby, who's one of our principal software engineers, also based in Manchester in the UK. So you see we've brought a pair of Daves. You probably know that an extra copy for redundancy is always good. And we're also eventually consistent in that he gets things straight away and I get things eventually. That's it for my database jokes. That's all I've got. So this is going to be a very broad talk going across the entire spectrum of Couchbase Server, and we'll dive into a little bit of the technical detail, but like I say, we will highlight the other talks where you're going to be able to get more information from the real subject matter experts along the way. This is an architecture talk, so if you're in the mood for block diagrams and rectangles, you're not going to be disappointed. We'll also try and freshen things up and show you a bit of a demo along the way. Try and keep it a little bit light. Okay, so let's get started. So you heard in the keynote how important customer experience is and how customers expect exceptional, incredible experiences whenever they interact with your goods or services or products. Understanding what the customer expectations are is one thing, but delivering to those expectations is another. You need your IT infrastructure and your organization to be able to adapt and to meet these increasing demands from your customers. And so I'm going to start with a very bold statement that absolutely everything we do in the Couchbase engineering organization is designed to meet these needs, to make sure that you can deliver the products and services that the customers need for that incredible experience. That's a little bit of a stretch. So let's take a look behind the curtain and see what this means in practice. So I went big budget on the Hollywood effect there. So Couchbase is a data platform. It's not just a database. It's not just a place to store your documents. It provides a rich set of services. You don't just want to be able to store your data. You want to be able to analyze it, to query it, to search it. Couchbase Server offers all of these services in a single platform, a single UI, a single piece of software to manage, to install, to run and maintain. We've always prided ourselves on our performance. So at the core of everything we do, performance, high availability, and scalability. And we want to make it as easy as possible for the developers to take advantage of these features. So we're a document database at our core. We're built on JSON, which puts the developers back in control of the data model. You want to add more fields to your data set? No problem. Change your application code and you're good to go. And all of the services we provide have a simple and intuitive method to access them. A few years ago, when we were looking to add query capability to JSON documents, we had a choice. We could come up with our own new language to access and query JSON documents. But instead, we chose, instead of forcing our customers to understand and learn a new language, we chose the one that people already knew. And so we've implemented SQL for JSON documents as a way of interacting with the JSON documents. Applications are written in one of a rich set of developer kits, SDKs that we provide. So currently, Java and .NET remain our two most popular, most downloaded SDKs. But there's also C and Python and PHP and Node and Go. So with all these features at your disposal, you still get to develop the application using the software language that you would like. A lot of the mundane mechanics of running some enterprise software are taken care of for you by Couchbase. So how does your data get sharded? How does your data get replicated? How do you sync the data from your web apps with the data in your pocket on the mobile devices? Couchbase Server offers automatic sharding, automatic replication, and automatic synchronization with mobile. So that's less time writing the mundane infrastructure code and more time for the developers writing these great apps to deliver the customer experience. Okay. So I'm going to start taking a look at some of what we call the architecture highlights, some of the key fundamentals of our architecture that help deliver the performance and scale, etc., that you've come to expect. So the first one is about the flexibility with how to deploy these features. So we'll start with a simple, here's the first big set of rectangles. You're going to see this quite a few times. We'll start with a simple developer environment where I'm representing here, you have a single machine, a single laptop or virtual machine, and for development convenience, when you install Couchbase Server, just tick all the boxes. You can have all the services running on a single node. So that's a single VM or a single laptop that can run all of the data service, the search service, the query service, analytics, etc. So that's maybe how a typical developer might set up their system. Let's take a look in a QE environment, a test environment, where you might want to run it as a cluster and test some of the node failure, the high availability capabilities. So we've spun up 3 more nodes. And in this example, what we're doing is we're running the data service across all nodes, but then we're splitting some of the other nodes to run individual services. So just to illustrate that the flexibility and the control is in your hands, how you want to deploy it. We don't rely on, the cluster doesn't necessarily need to be the same set of hardware. So if you want, you can have machines with more memory to run your data service. You can have machines with more CPUs to run the query service. It's up to you. Let's take it one step further and look at what a production environment might look like. So we've spun up a few more pieces of hardware now. So we've got a 7-node cluster. I think we've got 3 running the data service, a couple running the index and Fulltext Search. So Couchbase Server lets you mix and match according to your use case to give you the most efficient use of resource. Each of these services can be scaled independently, and we refer to this as multi-dimensional scalability. If your data set grows, fine, you can add some more data nodes. If you start running more queries, add more query nodes. So that's the first aspect to appreciate of Couchbase's architecture. These multiple services, select only the ones you need, and you can scale them independently. So the second concept will be familiar probably familiar to those of you that have either developed an application against Couchbase or been with Couchbase. But it's one that's worth restating, and this is Couchbase's ability to automatically shard your data. So this is something that the cluster manager and the client SDK take complete care of so that the application doesn't need to worry about it. And what this does, it ensures that your data set is evenly distributed across all of your nodes. It allows your data set to be replicated for high availability in the event of a node failure, and allows us to seamlessly redistribute or rebalance, in our parlance, the data across more nodes that gives you the elastic scalability. So here's a quick example of how it works. I've got an application that wants to write this JSON document into a 4-node Couchbase cluster. So the cluster manager is, when you write a document to Couchbase, you write it into a bucket. That's the place where your documents live. The cluster manager shards that bucket into 1,024 pieces, or V buckets, virtual buckets in our parlance. And the cluster manager keeps a map of where each of these shards live on the respective nodes. So when an application first connects to a Couchbase cluster, the cluster manager pushes that map to the application, to our developer kit. So when your application tries to write a document, what we do is the SDK runs a very simple hash function on the key of that document. It's a very predictable CRC32 hash that comes up with one of those shard numbers, one of those partition numbers between 1 and 1,024. And so in this example, the key Connect 2017 maps to vbucket 27. And then very simply, looking up in the map that the cluster manager provided, we can see that vbucket27 lives on node C, and that's how the application knows which server to contact for that piece of data. So the good news is, having told you that, as a developer of Couchbase, you don't need to know. It's all handled for you by the SDK in conjunction with the cluster manager. And let's take a quick look at how we use this same technique to dynamically or elastically extend the cluster. So let's say my use case has grown, my data set has grown, and I want to add more data nodes. So let's bring a fifth node into the cluster. Now we have node E. And what the cluster manager will do will reallocate some of those shards from the original 4 participating nodes, and it's going to move some of the data, some of those shards or vbuckets, onto the new node. And what this means is that there's a new map. There's a new set of instructions for which shards live on each node. So again, the cluster manager will push this new version of the map. And so having added a new node into the cluster, when your application wants to read or write that document again, it goes through exactly the same process. It runs the same hash on that document key. It's a predictable hash, so it will always to the same vbucket. So again, it hashes to 27. But this time, when it looks up shard 27 in the vbucket map, it will see that this time, shard 27 maps to node E. And so it knows that there's a new server to access that data from. So again, this is the technique that we use that underpins a lot of what we do, the performance for the even distribution, the scalability whilst remaining online of adding and removing nodes if you want, and the redistribution of data, all through this publishing of a map to the server. We also replicate these shards and store them on different nodes. So in our case here, shard 27, we would take a copy of shard 27 and store it on a different node. So if anything happened to node E, we could promote that other node, change the map again and say, okay, shard 27 is now available elsewhere. So this is where we get our high availability in the event of a node failure as well. So it's an important concept to understand, but not necessarily one that you have to deal with. The automatic sharding is taken by Couchbase itself. Okay. And the third architecture concept I'd like to introduce you is how we move the data around the cluster. When you write a document to Couchbase, how does it get to the other services? How does it get to the index service, to the analytics service, to the Fulltext service? And the answer to this is what we refer to as DCP. So in a moment when Dave takes you through the services in a little more detail, you'll quite commonly see DCP as the entry point. So this is the changes feed. So it's high performance, it's in memory, and so when a document is written into Couchbase's in-memory cache, it will transmit it asynchronously across the network to all of the other services that you have enabled on your cluster that are interested in the changes feed on that bucket. Not only the internal services, but the external ones as well. So for example, our backup manager. Our backup manager takes its changes feed from via DCP. Each change has a sequence number allocated to it. And so if you take a backup of your entire data set, you get from 0 to a particular sequence number on one day. The second day, when you come along to take a backup, rather than backing up everything all over again, you can resume your backup from that sequence number that you last, so you can take an incremental backup. And what this means is a shorter time to be able to back up your data, easier to operate, etc. Okay, so that's 3 quick pieces of the architecture. The ability to dynamically choose and slice and dice your services, the automatic sharding and replication that Couchbase does behind the scenes, and the fast in-memory protocol that we use to push data around the cluster. Okay. So with that, I'd like to take a quick detour to show you what this actually looks like in practice. So I have a cluster running. I'm going to ask you actually to all get involved in this in a moment. So prepare your laptops or your mobile phones. Let me flip. Hey. It's not a great start to the demo, I'll be honest. Let me just check I'm still online. The Wi-Fi was a little sporadic this morning. Okay. Give me one moment. I'm going to kill the Wi-Fi and start again. Otherwise, I'm going to have to give the demo a wide berth. We'll get into the next bit. All right, it looks like we are in business, he says. Okay. Let me log in again. Apologies for this. I hope you're getting the impression that this is authentic. This is a live demo. That's what you've come to see. Not strong marks for interest, but maybe strong marks for authenticity. There we go. Okay. All right. So this is the Couchbase Server 5.0 UI. First time as well. Perfect. So in my cluster, we're running 3 nodes. You can see that these nodes are running a mixture of different services. So the first node is running the data, the index, the query service. Second one just running the data service, and the third is running both data and full text. So I would like at this stage, again, to show you that this is all live, if you didn't already believe that, to generate some data, to load some JSON documents in. And just to do that, I'd like to invite you to visit that URL if you can and come to the shop. So if you've got your phone or your laptop out and you're on the Wi-Fi, then bit.ly/cbconnect17, and you should be presented with this page. And when you get there, what I'd like you to do is place an order. So you can add if you add your name and your company name, and select exactly 5 items, no more, no less. That's how this demo works. We have a simple shop with some tremendous, the finest of British produce. Whoops. So 5 items, and submit your order. And you should see, we should hopefully see some of those orders coming through. Start a revolution. Nice, nice. So I've gone for some apples, some cheese. Dale Rob, where's Dale Rob? Hey, Dale, thank you very much. You went for some Marmite. Nice. You British? No. Do you know what Marmite is? She knows it's gross, yes. Neil's gone for the fish fingers. Okay, so let's flip back to the cluster. We have some orders coming in, so we should be able to take a quick look, and we'll see. Okay, so each of these orders that are being placed on the website are generating JSON documents. So BHC test, it was BHC test. There you go. What have you gone for? Oh, lovely. A questionable diet, I would say, sir, of eggs, bananas, Scotch egg, and fish fingers. Halloween party, perhaps. Okay. So there was a simple website generating JSON documents into a Couchbase 5.0 cluster. Now let's look at being able to run a query on this. So I have some queries prepared. So hopefully, again, this is all embedded in that single management interface in the single UI. And I mentioned these are JSON documents, and we're going to run a SQL-style query on it. What we're going to do here, because JSON has a slightly richer structure than SQL, we've extended SQL with the unnest clause that you'll see there. And so what we're going to do, we're going to look at those JSON documents that you were just creating, the shopping baskets. We're going to extract all of the items from your shopping baskets, sum them all together, and see amongst you what the most popular products were in the room. So if we run this now, number 7, fish fingers. Fish fingers and a Scotch egg. So hands up, who knows what a Scotch egg is? Oh, a few people. It's a boiled egg covered in sausage meat and then in breadcrumbs, often used on British picnics. So it's not a particular delicacy, but there you go. It's a popular one today. One final query, just to show you. So this time we're going to bring the concept of SQL's join to bear on JSON documents. So we're going to find out each of these items was secretly given a price, and we're going to find out who placed the most expensive order here in the room. And in order to do that, we're going to join the documents from your order, your shopping baskets, join those with the product items that we have that contain the price, sum them up together, sort them, and see who had the most expensive. Martin Freeman. That was yourself. Congratulations, sir. Your order of bananas, cheese, milk, Scotch egg again. It's got a lot of Scotch egg connoisseurs in this room. Very good. Okay, so there you go. So hopefully you get the idea. Couchbase, single platform, JSON documents coming in, being able to run SQL-style queries across the data. One thing I would like to show you is our, again, I have a phone here, and what I would like to do, so I don't know if you'll be able to see this live, but as I'm scrolling on the phone, this is very thanks to my colleague Matt, whose phone I've borrowed. Again, let me log in. And I want to show you the automatic mobile synchronization. So if I run, I might need to like that? Confirmation. So what we're going to do here, if we find some drinks on the mobile here, what we're doing here is running the same SQL-style query on those JSON documents. This time the SQL query is going to update a subset of those documents. And when we hit execute, if you keep an eye on the drinks, so you can see the beer towards the top of the phone. So this is combining what we should see, if that's synchronizing. Okay, I don't think the phone's lost the Wi-Fi as well. Okay, never mind. The other service I'd like to show you is search, so you can see, as well as being able to query documents, we can run Fulltext Search on them. So instead of, if you want to look for engineers, that will also find the documents that contain things like engineer, engineering. So Fulltext Search understands the stems of words and how they are constructed. So if we search this, and it does things like syntax highlighting, and you can see if we go back to our shop. So I'm going to deliberately mistype bananas. And this is one of the powers of sort of full-text search over and above query. It can do sort of search fuzziness rather than specific things. So again, hopefully that gives you an overview, a rich set of features, single place to manage them, and manipulating on JSON documents. Now, to take you through some of these features in a little bit more detail, I'd like to introduce you to Dave Rigby, who's going to walk you through each of the architecture of each of these features in more general. Thank you, Dave.
Thanks, David. Okay. Okay, so we've given an overview of how the architectural features work. We've seen a demo of most of it in action. So I want to dig a little deeper into some of the main components to give you a bit more of a flavor of how they actually work. So the first of these is the Queston Manager. So as the name suggests, the Queston Manager is responsible for the management of all nodes and all the services running on those nodes. The main functions of a Queston Manager are cluster membership, which nodes are in the cluster, adding and removing nodes from the cluster, status and health monitoring of those nodes and the services running on them. Is that node got correct connectivity? Is its disk okay? That kind of thing. We saw how we have different services and we can put those services on different nodes. So the Queston Manager is responsible for the layout of those services, making sure they're running on the correct nodes in the cluster. Responsible for data placement. So again, we saw how we have but bucket is broken into 1024 vbuckets, and we always have one active set of that. We might have 1, 2, or 0 replicas in some instances, and it's responsible for making sure that those active and replica vbuckets are in the correct place. Obviously, you don't want to put a replica in the same place as the active, or it's not giving any resiliency. And then related to that, it handles rebalance. So when we have to move the data around, when we're adding or removing nodes from the cluster, we redistribute those vbuckets. And it's responsible for failover. So failover is when we detect that a node is problematic, we can automatically fail that node over. So we promote a replica in its place. In 5.0, this is one of the areas that's new. We've added a new fast failover. So we've improved the failure detection mechanism. So we've got more inputs into the failure decision process. And as a consequence, we can detect that failure and failover much quickly. So we can now do that in under 10 seconds. It's also responsible for authentication. And RBAC is a new feature in 5.0, so we can use role-based access control to give us finer-grained authentication, so giving specific roles to specific users. And as we've seen, we have a user interface which has been refreshed in 5.0, making it easier for you to operate, and the admin APIs. So let's go down one more level. So the Queston Manager is implemented in Erlang OTP. So Erlang, if you're not familiar, is an actor-based distributed concurrent programming language. And this is well suited to a task like a distributed control plane like the Queston Manager. Each actor, or the Erlang process, as Erlang refers to them, handles a specific task, using message passing to communicate between them. One of the advantages here is because we're using message passing, talking to a local process and talking to a remote process is exactly the same. This simplifies a lot of the problems normally you would give in a distributed system. So at the top level, we have the main things the user interacts with. We have the admin console and the REST API, and alongside that, we have authentication. Below that, we have master services. So we said earlier that we have the same thing installed in every node, and that's completely true. But there's certain processes or tasks that only actually execute on one node. So we will elect an orchestrator or a master node in the cluster, and that is the one that's responsible for making some of these key decisions, such as data placement, rebalance, and auto failover. Alongside that, we have things like bucket services. So we have an instance of bucket services for every bucket. These handle things like DCP management, making sure that a bucket has DCP connections going to the right places, and stats collection and monitoring, which is presented up to the UI. We also have per node services. So these are, as the name suggests, things that run on each node, things like heartbeats to make sure the nodes can talk to each other and we can identify if there's any networking issues. And the babysitter process, which is responsible for keeping an eye on the actual processes running, so the different services in each node. And then below this, we have some generic distributed facilities, things like the global configuration, which is replicated using gossip replication. And we have distributed node discovery. So again, when we're adding new nodes to the cluster, we need to discover those nodes on the network. And then there's some local facilities, so local configuration, working logging, and similar other services. OK, so that's the Queston Manager. So I'll now talk about the data service. So if the Queston Manager is the control plane of Couchbase Server, then the data service is essentially the low-level data plane. And it provides key value access. So if you know the key to a document, you can ask the data service to give you that document. You can get a full document, or you can get a sub-document. So you may want a particular field or subfield of a JSON document or an array element, and you might want to mutate only that one element or look at that array element. Architecturally, the data service is an evolution of Memcached. We've subsequently added persistence, replication, enhanced data APIs, and other such similar other things as well. It's a source of DCP. It's the place where the DCP is produced and we distribute it around the system. MapReduce views are also part of the data service. And we have three bucket types. We have a Memcache bucket type, which again is backwards compatible with Memcache. We have a persistent bucket, sometimes called a Couchbase bucket, which you're probably quite familiar with. It's the main one people use. And new in 5.0, we have a new ephemeral bucket type. This is a purely in-memory bucket type. So if your application doesn't require persisting to disk, you can keep the data set entirely in memory. You don't have to have the overhead or cost of managing disks. So let's drill into what's actually going on underneath here. So at the top end, we have the listener. So we have a set of asynchronous, multi-threaded pool of threads which handle networking, authentication. We have a very scalable system here. We can handle tens of thousands of current clients at once and service them all with low latency. For each bucket, there'll be an instance of KV engine. This is a database engine, and this is where our kind of memory-centric data store works. We have a set of partition hash tables for each vBucket, and this is where mutations will be accepted and stored, and where requests for hot documents, popular documents, will be served directly. Below that, we have a checkpoint manager. This is responsible for creating ordering of these updates. So given we're replicating this data across the cluster, we need to make sure we have a consistent view of that data in all different services. So we need to make sure that there's a guaranteed ordering, and it also means that we can resume from the same place and continue where a service might have left off. David mentioned this could be used for backup, but it's also useful if you have some kind of like a network issue or you're bringing a new service online. The fact that you've been interrupted means that you can still resume from where you previously were. Alongside this is a number of asynchronous tasks that run in the background. So we try to minimize the amount of work that's done on the sort of a front-end request thread that the client operation is served from. We have the item page and expiry page, which is responsible for removing items from the managed cache. So either because they are no longer hot and we don't want to waste memory on keeping them in memory, or because they've expired and they should be deleted. On the disk side, we have a flusher and a background fetcher. So the flusher is responsible for flushing batches of mutations down to disk system. And the BG fetcher is kind of doing the reverse. So if we have a request for a document which isn't resident in memory, we'll bring it up using a BG fetcher. And all this runs on a scheduler which has a set of thread pools for each of these different tasks. So we can kind of try and prioritize these tasks to minimize how long it takes to perform the front-end operations that users care about. Okay, so the next service I'd like to give you an overview is a query service. So the best way to summarize this is it's SQL for JSON documents. We saw an overview of this earlier. So Nickel is an evolution of SQL. What we've tried to do is only change this from SQL where absolutely necessary. So when there's a concept, the fact that the document might have different fields, it's heterogeneous, or the fact that it has nested data, we need to add some new keywords to be able to deal with this, as we saw. So we've given you a very familiar language. It should look like SQL, very similar. There's a few bits that will be different, but it essentially looks like SQL. So let's get a quick kind of run through of how a request runs through the query service. So the client will make a request. It will begin to front of the query service, and we'll first parse for correctness and plan to how we're going to fulfill this query. The plan is deciding things like what indexes have I got, which index is most suitable for fulfill this request. And for common queries, this can be stored, so we don't have to replan every time. There'll then be a scan phase. So using the indexes we've identified, we'll scan that index, we'll get information about the documents that match this particular query. And then we'll actually fetch the data that is part of those particular documents from the data service using the key value API. We then go through a kind of a pretty normal kind of SQL pipeline. You know, we'll perform filter and aggregation, we'll sort the data, and we'll return that data to the client. It's heavily parallelized, so we can take advantage of all the cores that are available on each query node. So you can scale it, and again, it's an MDS service, so we can scale this as appropriate independently of the other services. So Keshav is presenting immediately after this session, actually, on what's new in 5.0. So he can give you a lot more information on what we've added recently to Nickel. Okay. So one of the things I just mentioned, which query is built on, is global secondary indexing. GSI is essentially the power behind efficient queries. By allowing us to define indexes on particular fields, we can give lower latency and higher throughput than just doing a scan of the whole bucket. Again, given it's an MDS service, we can isolate key value operations where we don't want to impact their latency. There's two main types of indexes you can define in Couchbase Server. You have memory-optimized indexes. These are suitable when your indexes can fit entirely in memory. And these can take advantage of the fact that there's no I/O path, so they can give you higher throughput and a lower latency. We also have standard indexes, so if your index is larger than memory, then we will store them on disk, but we will still cache the most frequently used part of those indexes in memory, so maximize the performance of them. And in 5.0, we have a new storage engine, which we call Plasma, which uses a local skip list for the disk to give you a highly concurrent data access when going to disk for the index. So again, a very quick through. Part of the indexer that lives on a data service, this is a projector. This is basically taking in DCP streams and trying to answer the question, is this change relevant to the indexes that exist? It knows what index exists. A document might change which isn't relevant to an index. We don't want to bother sending that information to the indexer if we don't need to. It also might find something is relevant, but we need a subset of that document, so we can optimize what we send over the network and give the indexer slightly less work to do. The indexer has a supervisor, which manages the indexes that have been defined, and then coordinates scans coming from the query engine. We may have to service that scan from various indexes. And then we have the storage engine I mentioned when we're storing things to disk. So again, this is probably the most curiously titled talk of the day. Venkat has indexes the Batman of the data world, so I have absolutely no idea what Batman's got to do, but maybe you can find out at 2:30. Okay, so I'll briefly talk about Fulltext Search. We saw this in action just before. This is now out of beta, and it's GAing in 5.0. So this is, I think Googling for your JSON documents is kind of a one-liner for this. You have an application that has an open text area for free text search, your Google search, Amazon product search. And users can type in what they want, a customer name, a username, product. And which problem we're trying to solve here is, what did the user mean to search for? They didn't necessarily enter that. They might have got the wrong name. They might have spelled it wrong. They might have asked for plural when there's actually a singular name. And we also want to decide which is the best match for them. It isn't necessarily a Boolean thing. Let's look at how this works. We have a REST interface as much of the system, which is used to define indexes. We want to define what fields we're going to index and how we're going to search those fields. More on that in a second. So the indexes are partitioned, very similar to what we saw previously with the vbuckets. So we can get the same availability by having multiple copies and scalability by moving where indexes live as the number of nodes that FTS is running on change. So the actual indexing work is done using a component called Bleve. This is a standalone Golang full-text parser developed by Couchbase. And it uses an algorithm called TF-IDF. The thing that TF-IDF gives us is the ability to score results. So this is how we can actually rank results based on their relevance or their perceived relevance to what the user has to do. And this gives us things like the fuzzy searching that we saw earlier. It also handles things like different natural languages have different rules. So what do you consider to be a plural might be different in English compared to another language. Or what a suffix might be. You might want to remove an ing suffix from a word because it's not actually part of the core noun that you care about. It also handles things like white space rules. So if you're searching for an email address or a URL, you don't actually want to break on the individual couchbase.com separators. You want to treat that as a single term, which might not be the case if you were searching a free-form text string. And so Marcy at 345 has a talk on telling you how you can enable full-text search for Couchbase documents in your cluster. Okay, finally, I want to talk about the analytics service. So analytics service, which is still currently in developer preview, extends Couchbase data platform to allow you to perform near real-time analytics queries. It does this using a query language called SQL++. It's quite similar to Nickel in some respects, but it builds on SQL but adds features for deploying analysis on JSON documents. We use the same DCP protocol, so this gives us fast data synchronization. This is important for analytics because it means you've got near real-time copy of that data. You're not operating on a copy that was ingested by a batch job maybe some time previous, and so you've got up-to-date results. It allows you to do ad hoc queries. You don't have to create an index up front. You can just create the query and ask me anything. And again, we have the same workload isolation and scaling we have using MDS. So how is this structured? Well, at a very, very high level, we have DCP to ingest the data. This brings it into a data format called a shadow set. This is actually a restructuring of the same data that's optimized for analytic organization so we can perform effective aggregation, indexing, and query processing on that data. We can persist data more longer term than we might do in the actual main data service. So we might have data that's expired or deleted. We may want to keep, for analytical purposes, data for a longer period of time, and we can do that in the shadow set. And given this is a separate analytics MDS service, we're isolating it again from the other services. We're minimizing any impact any of the services have on each other. And again, we've got a talk at 4:30 this afternoon where Till will give you an overview of how you can actually use this to perform analytics on your data. Okay, so that's a very whistle stop. I had to also pull it in because we ran a bit late on the keynote. But there's a whistle stop to all the main services. I'll hand you back now to David.
Fantastic. Thanks, Dave. Okay. It's just about us at the end. So what have we learned? We've learned that doing live demos that rely on Wi-Fi are often prone to interruption. We've learned that Marmite is gross. We've learned that Scotch eggs are surprisingly popular. But also, hopefully, you've learned a little bit about our architecture and how we're a feature-rich data platform, all managed under a single product that delivers a variety of services that are all architected to be scalable, performant, and highly available to help you deliver those fantastic, incredible experiences to your customers. Dave and I will be hanging around for questions after, during the break. But until then, thank you very much. Cheers.